Welcome to UGC lecture series Linear Integrated Circuits. In this lecture, we are going to discuss about the AC characteristics of operational amplifier, and the AC characteristics are frequency response, stability of op amp and slew rate. In the last lecture, we have seen the DC characteristics, and they are nothing but the factors which are responsible for producing the output in the op amp when no input signal is given. And we have seen the compensated techniques to make the output 0 if the input signal is 0. But those compensation techniques works for only DC signals. What will happen if the AC signal is given for the operational amplifier? So, where the frequency response will get affected. For actually the ideal characteristics of IC 741, that is the operational amplifier, is the voltage gain is infinite. If the voltage gain is infinite and bandwidth is infinite, then the gain of the op amp for DC signal and AC signal must be equal. It has to be constant if AC signal or DC signal is given as the input. For example, if the gain of the op amp is 90 dB for DC signal, and if you apply AC signal, then the gain will get reduced at the rate of minus 20 dB per decade, which means that for 10 times increase in the input frequency, the gain is decreased by 20 dB. What is the reason behind this factor? Actually, there is a capacitance effect felt at the output of the operational amplifier. This is because the physical characteristics of op amp as well as the constructional features of op amp will produce many capacitance effect in its circuit. And we are considering all these capacitance effect as a single capacitor, and which is shown in the circuit. This capacitance is actually it is not actually connected, which is a effect seen by the operational amplifier at its output. Here this triangle is the operational amplifier, for which the two input signals are given V1 and V2, and the R0 is the output resistor, and this capacitance is actually not connected, but due to the physical characteristics of operational amplifier as well as the constructional features of operational amplifier, there are many capacitance effect present in the circuit, and which is considered as a single capacitor at the output. So, this capacitor makes the change in the gain, and which is reducing the gain by minus 20 dB per decade. Calculate the gain, and before that we have to calculate the output for the equivalent circuit we have seen. So, consider the input signal as Vi and the output where we are having a capacitor which can be given as 1 by Cs in S domain divided by 1 by Cs plus R. And here if you replace this S as j omega and simplify this equation, then you will be getting Cs and Cs will be nullified, and the final value is 1 by 1 plus RCS, where input signal is multiplied with this factor, and if we take the gain, then it is simply 1 by 1 plus RCS, and substitute S is equal to j omega, which gives you j, and omega is 2 pi f. So, again you substitute 2 pi f, it is j 2 pi f RC, and this can be written as f by f1, where f1 is 1 by 2 pi RC. So, this part is taken as f1 1 by 2 pi RC, this f is kept as such. So, the final equation, that is the gain, is 1 by 1 plus j f by f1. When you see the circuit, actually we have calculated the gain from this point to this point, that is the output of the op amp to the output of the circuit. So, here we have taken the input as Vi and output as V0. So, we have derived V0 by Vi, the gain, as A, which is equal to 1 by 1 plus J f by f1. And there is a operational amplifier here, this gain is also included with this equation as AOL. AOL is open loop voltage gain. And we have considered 3 frequency values, or you can say we can compare this frequency f and f1. What is f1? It is the corner frequency or the breakover frequency, and f is the frequency of the input signal. So, which is compared, the frequency of the input signal is compared with the breakover frequency f1 here. For the first case, if the frequency is less than f1, if the frequency is less than f1, what will happen to the gain? See here, for which we have to take the mod value of the gain. So, it is AOL divided by root of 1 plus, that is a square plus b square, that is the real term square plus the complex term square, which is given as f by f1 the whole square. So, in this case, if you compare these two frequencies f less than f1, what will happen to the gain of the entire circuit? If f is less, then you can neglect the denominator portion and you can equate these two gain. Gain is actually the constant value AOL, which is depicted in the picture given here. So, from this graph which shows the input frequency in the x axis and the gain at the y axis, and this graph is called as Bode plot. So, one is the frequency versus gain and next one is the frequency versus phase in the circuit. So, for the first graph we can see the relationship with the input frequency and the breakover frequency and what is happening for the gain of the operational amplifier. For the first case, we have seen f less than f1. If f is less than f1, from 0.2 f1 up to this value, the gain is constant. We have actually seen before in the equation. So, gain is constant, and what will happen if f is equal to f1? If f is equal to f1 according to the equation, according to this equation, if f is equal to f1, then the gain is actually AOL divided by root 2 if these are equal. If it is root 2, then if you take dB, in terms of dB, it is minus 3 dB. It is actually reduced. So, at f1 it is minus 3 dB of the previous value AOL. And what is happening after f1? If the frequency is still increasing after f1, so if f is greater than f1, the gain rolls off at the rate of minus 20 dB per decade. So, we can see in the equation also, if f is greater, then you will get a greater portion here and this 1 is neglected, and if you take the square root, then you will be getting a numerical value which is increasing if the frequency of the input signal is higher, and if the denominator portion is increased, then this value will get divided by the greater value. So, ultimately the gain of the op amp is reduced, which is shown here, and it is reduced at the rate of minus 20 dB per decade. And this is what we can discuss in the frequency response curve. And for the next curve, the equation is minus tan inverse of f by f1. Again we have to compare the equation f in this equation f and f1. F is the input frequency and f1 is the corner frequency or the breakover frequency. For the first case, if f less than f1, or you can say f is equal to 0, then theta is actually 0, which is given here. If f is equal to 0 and the phase angle is actually 0, so the curve is starting from 0. And for the second case, if f is equal to f1, if f is equal to f1 at this point, then theta is, or the angle is minus 45 degree. And for the third case, if f is greater than f1, or you can say f is infinity. If f is infinity, then here infinity is, it is not shown in the graph, but it is understood that if f is increased to the higher value, then theta or phi is taken as minus 90 degree. So, this is the maximum phase shift produced in the operational amplifier with a single capacitor. So, if a single capacitance effect is considered, then the frequency is reduced at the rate of minus 20 dB per decade, and the phase shift is considered as, maximum phase shift is considered as minus 90 degree. What will happen if 3 pairs of RC is considered in the output of the operational amplifier? The graph shows that the frequency in the x axis and the gain in the y axis, and there are 3 corner frequencies because of 3 RC pairs. So, this F1, F2, F3 are the frequencies obtained by 3 RC pairs, and up to this F1 the gain is constant and it is 90 dB per decade, and after this F1 the gain is reduced at the rate of minus 20 dB per decade up to F2, and after F2 it is again another minus 20 dB per decade, and after F3 another minus 20 dB per decade, and finally if 3 capacitances are considered, then the reduced in gain is 20 plus 20 plus 20, finally the 60 dB per decade, and the gain is actually 90 minus 60, 30 dB per decade. Similarly, the phase shift will also be increased. It is for a single capacitor it is maximum minus 90 degree, for a 2 capacitor it is minus 180 degree. So, this is the frequency response of the operational amplifier when an AC signal is given. And the next AC characteristics is the circuit stability. So, the circuit or a group of the circuit connected together as a system, and if it is stable, if the output reaches a fixed value in a finite time. If it is unstable, it is unstable if it takes time or it does not reach the output. This is a simple example of a system, and we are taking it as a voltage follower circuit. Here the input signal is given to the third terminal and a feedback signal is given to the second terminal, and output is taken at the sixth terminal actually, and here there is no resistors at the input and at the feedback. So, what is the input given? The same input can be feel at the output terminal. The same voltage follower circuit is redrawn like this for considering the stability of the operational amplifier. The input signal is given to the positive terminal of the summation point, and the output is fed back to the negative terminal, and both are summed up and given to the input of the operational amplifier. Actually, this is a loop formed from the output to the input. This is a closed loop system. So, from this these two figures are one and the same. These two diagrams are one and the same here. This is the gain of the amplifier A, and B is the feedback factor which is given to the negative terminal of the summing point. So, from that standard system or a closed loop system, we can get an equation called ACL is equal to that. ACL is the closed loop gain, which is given as A by 1 plus A beta, where A is the amplifier gain and beta is the feedback factor. For a stability of the operational amplifier, we have to see the characteristic equation of this closed loop gain. The characteristic equation is 1 plus A beta, which is equal to 0. This is the characteristic equation. At one point, the magnitude A beta will become 1. And the phase shift in the circuit will be equal to 0 or multiple of 2 pi. Since we have a capacitance, we know that if the capacitor's effect is considered as 2, then for a single capacitance it is minus 90 degree, and for a 2 capacitor it is minus 180 degree. If the circuit is an inverting amplifier, then the inverter will actually give you 180 degree phase shift, and this capacitor, two capacitors will give another minus 180 degree phase shift. Both will get cancelled and the phase angle will be equal to 0 in that case. So, this will become a problem for a stability of an operational amplifier. So, we have to do a compensation technique, which is the concept of the frequency compensation. So, here if the capacitor is considered as a single capacitor, that the gain is reduced only at the rate of minus 20 dB per decade. If we consider the 2 or 3 capacitors, then the phase shift is minus 180 degree practically for a 3 capacitors effect. So, the compensation techniques which are used for ACE signal as the input of the operational amplifier, which makes the capacitors effect as single capacitor, and the gain is reduced only at the rate of minus 20 dB per decade instead of another 20 dB per decade for the next capacitance effect. So, there are two compensation techniques basically. One is the external capacitor, external compensation technique, and the next one is internal compensation technique. In some operational amplifiers, there will no any internal compensation for a AC characteristics. So, in that case we have to add externally some passive components to compensate the frequency response of an operational amplifier. So, external compensation techniques are dominant pole and pole zero compensation. The first one is dominant pole compensation technique, and this dominant pole, which is nothing but the pole term will be introduced in the gain of the operational amplifier. So, here this A is the gain of the entire circuit and AOL is the gain of the open loop operational amplifier, and which is divided by 3 frequency terms, that is 1 plus JF by F1 is the first frequency term for a single capacitor, and another term called F2 which is for the second capacitor, and F3 for the third capacitor. So, in this example we have considered that there are 3 capacitors at the output of operational amplifier. So, there are 3 frequency terms in the gain of the operational amplifier. So, this is actually the circuit in which we are going to do some compensation. So, here this is the operational amplifier for which the input signal is given as V in and the output is considered as VO dash, and after which a resistor is connected, and across the resistor at the end of one end of the resistor we have a capacitor. These two passive components are connected to have a dominant pole in the output of the operational amplifier, or you can say the gain of the operational amplifier. So, the entire circuit's output is represented as VO. The gain is derived as A1 is equal to 1 by 1 plus J 2 pi F RC. So, the similar type of equation we have derived just now for calculating the gain of the operational amplifier in the case of frequency response. So, in the same way we have to derive the gain of the operational amplifier with this R and C which we have connected externally to produce a dominant pole at the output. So, in this case we have got 1 by 1 plus J 2 pi F RC. Here F is kept as such and the remaining terms are considered as FD equal to 1 by 2 pi RC, and A1 is 1 by 1 plus JF by FD. So, here FD is the dominant frequency term which is going to decide the gain is reduced at the rate of minus 20 dB per decade. After compensation, R and C is after giving R and C at the output of the operational amplifier, and if we derive the gain of the operational amplifier, we have another term called 1 plus JF by FD which is included in the gain of the operational amplifier. So, this graph which tells you the reduction in the gain, which tells you the reduction in the gain at the rate of minus 20 dB per decade only. So, when you look at the the graph for the uncompensated operational amplifier, this line, this is the uncompensated operational amplifier, this line. So, the AOL is constant for some frequency and after this frequency it is reduced. This is actually minus 3 dB line, and it is reduced at the rate of minus 20 dB per decade, again another 20 dB per decade, finally it is minus 60 dB per decade totally. So, if you compensate with the RC pairs at the output of op amp, the gain is reduced only at the rate of minus 20 dB per decade, and it touches 0 dB at F1 itself. Say this is F1, this is F2 and this is F3. So, the gain is only decreased at the rate of minus 20 dB per decade, and it touches 0 dB at F1, only one corner frequency, and the 3 capacitance effects is nullified here, and only one corner frequency is considered here. So, actually the bandwidth this for the compensated op amp it is bandwidth 2, for the uncompensated op amp it is bandwidth 1, and bandwidth is reduced. This is the demerit produced in the dominant pole compensation. Okay, the merits are excellent noise immunity system as the bandwidth is small, and by adjusting FD, that is the dominant pole frequency, the phase margin and the stability of the system is assured. The bandwidth is drastically reduced for a compensated system, and this is the disadvantage of the dominant pole compensation. The next one is pole zero compensation. So, what we have do in the dominant pole is we have created a pole term in the gain of the operational amplifier. In in pole zero compensation, we are going to create 2 terms called pole and zero in the gain of the operational amplifier. So, this is actually the same formula what we have seen in the dominant pole compensation. Initially, without any compensation, the gain is written as A equal to AOL by 1 plus JF by F1. This is for the first capacitor, and 1 plus JF by F2 for the second capacitance effect, and for the third capacitance effect it is 1 plus JF by F3. So, this equation is for the op amp without any compensation, and this is the compensation we have included with the help of the resistors and the capacitor R1, and in this case we have just included R2 in series with the capacitor C. So, this is the change we have made for pole zero compensation. So, for which if you derive the gain of the operational amplifier, then it will be like A1 is equal to Z2 by Z1 plus Z2. What is Z2? This is Z2, R2 plus C, and Z1 is R1. So, if you substitute Z1 and Z2 in this equation, you will be getting this term 1 plus J2 pi F R2 C2 by 1 plus J2 pi F into R1 plus R2 C2. So, here only the resistor R2, and here the resistances are R1 plus R2 in the denominator. So, the F1 term is 1 by 2 pi R2 C2, and F0 is 1 by 2 pi R1 plus R2 C2. So, this is the F0, F0 is the 0 created in this compensation, and F1 is the pole created in this compensation. So, A1 will be 1 plus J F by F1 by 1 plus J F by F0. This is included in the uncompensated operational amplifier, so that the op amp is now compensated. So, we have to include this term with the initial gain of the operational amplifier. If you include this, the term which is present in the numerator is the zero term, and the term present in the denominator are the pole terms. So, here a zero term is created, here the pole term is created. So, zero term has the frequency F1 and pole term has the frequency F0. The other 3 frequencies are F1, F2, F3 due to the 3 capacitors present in the op amp. So, the relationship between the frequencies are F3 must be less than F2, and which is less than F1, and F1 must be less than F0, and F0 must be greater than 0. So, F3 must be greater than F2, F2 must be greater than F1, and F1 must be greater than F0, F0 must be greater than 0. So, this is the relationship between these 4 frequencies. When you look at the graph for pole zero compensation, this line indicates the uncompensated operational amplifier. This graph indicates the uncompensated operational amplifier, which we know that up to F1 it is constant, and after F1 until F2 it is decreased at minus 20 dB per decade, and up to F3 it is minus 40 dB, and after F3 it is minus 60 dB per decade. So, when you compensate with the pole and 0, then you will have a term called F1 in the numerator and F1 in the denominator also. So, these two terms will get cancelled, and so in this graph you see that after this FO, that is the first frequency, the gain is reduced at the rate of minus 20 dB per decade. Instead of touching at F1, it is going to F2 and it touches the 0 dB line. So, only at F2 it touches the 0 dB line. So, in the case of dominant pole, it will be touching the 0 dB line at F1. In the case of pole 0, it is touching the 0 dB line at F2. So, that is the difference. So, we have a greater bandwidth when you compare with the pole 0 compensation. In internal compensation, 30 picofarad capacitor is connected at the output, and this type of compensation is called the Miller effect compensation. And these are the operational amplifiers which have internal compensation for frequency response. So, we have seen and discussed about the frequency response of operational amplifier, stability of operational amplifier, and slew rate we will be discussing in the next session. Frequency compensation techniques we have discussed, and these are the questions you can answer for this and the references. Thank you.